expressed the concern that they need some more help on homework. And I would like to reiterate that I am available just about most of the time during the day. If you email me, I will try to email you back pretty quickly. And I can email back not just with some words and some text in a box that you read, but I can also send you little EduCreations recordings, little whiteboard recordings if you need help with a problem and it needs to be sketched out somehow and made visual. So be aware that I am available to help you with things each and every day. The only day that I take off completely from helping students is Sunday. Sunday I spend with my family without distractions. But every other day, including Saturdays, I try to check my email at least a few times a day, usually several times a day, and answer questions for students. Another couple of resources that you may want to remember, we talked about these at the very beginning of class, is if you go on to WebAssign, right next to the Assignments tab, there's a Resources tab that you can click on to look at different things. Let's see, do they have one? Oh, let's fix that. I'm still working on getting things all set up here. Let's see, what's it looking at here? I need to go this way. There I am. Oh, there I went. This room is so dark. Of course, the lights didn't turn on when I thought they would. The light switches are all backwards and funky. We actually didn't talk about the Resources tab because the resources there are not that great for students. But if you do go to, actually I do have some of them available. Let me take a look at the student view really quick, see what you can see from there. So it's so you get a thing that says My Assignments, and then at the bottom there are resources at the bottom of the page, and then you click on that, and each chapter has resources, so you can go and take a look at PowerPoint slides that the company makes, but you can also look at the PhET simulations. Those are sometimes helpful. And let's see, what is this? They call this Join In. This is a new thing, so I've not used it before. Protected view, slideshow, from the beginning. I don't know if they have anybody speaking during this. Let's see if they do. Looks like they don't. But they do have some like PowerPoint lectures here if you're interested in looking at how they present things in some of the chapters. They present things a little bit differently than I will, but it's still the same stuff. So there are resources, but there's one more resource that I want to show you that you may not be aware of. I don't think I've mentioned it. If I did mention it, it was probably at the very beginning of class, and I apologize if I have not mentioned it since. But if you can get into Blackboard, you can get into Blackboard as a student by using your central login for Mid-Plains, which is your email address for your username and then your password for your email account. Put your password in here, whatever it is. And then you can sign in and it will get you into Blackboard. And in Blackboard, if you go to somewhere, I think I erased it from my front page, so I have to go back and find it again. Anyway, in Blackboard, if you are a student, for sure you will have this. I don't know why it's not showing for me, it usually does. But you should get a thing down here that says BrainFuse. It's an online online tutoring that is free for MPCC students. And like I said, I don't know why it's not showing up on mine, but it should show up on all the students. And BrainFuse is live online tutoring with online tutoring with real tutors, real people who know the material. So, and I've had students use it in several different classes and have success with it. So it's not hard to use. I was hoping that I could kind of open it and show you it here, but apparently it's not going to let me show it here. And hopefully that it shows it in yours. It should be in there. But yeah, BrainFuse is available in Blackboard, in PCC's Blackboard page. So another resource for you. Also, if you're here on this campus in North Platte, then we do have tutoring available down in the Success Center. I don't know if they have a dedicated physical science tutor right now. But you're also welcome to come to my office and I can help you there. So, anyway, just some resources for you. Make sure that you avail yourself of those resources. Make a great effort to talk to me first. I can help you with these things better than anyone. So don't be shy about asking your questions. I guarantee you there's more than one person that has that question that you're not asking. Okay, so let's talk about today. What is today? Today is the 17th. So we have some homework due today, apparently. Chapter 7. And that is, we're still in optics. We're going to optics today. Did we do chapter 6 last time? What were we doing last time? No, we were doing optics last time. I remember now. So we're in our optics thing here. We started with, we got to a little bit, we started talking about ray tracing a little bit and mirrors a little bit. I think we were right about in the 170s. Let's take ourselves there really quick and see where we end up. I don't think we quite got to our spherical mirrors. We were definitely talking about flat mirrors. And we talked about dispersion of colors and the rainbow. We didn't really talk about the actual rainbow, what makes rainbows happen. We started to talk about these dispersions of colors. So let's get back to this a little bit. This phenomenon where you can split light, white light, into many colors, and you can split other lights into colors as well. But it just kind of depends on what kind of light it is. But purely white light is really just a mixture of many different frequencies. And when you put all those different lights, all those different wavelengths of light through an optic of some kind that causes it to bend the light, each one of those lights, each one of those frequencies or those wavelengths is bent at a different angle. And the reason is because each one of them has a different wavelength. So the longer wavelengths tend to be bent less, and you can see that here. The white light comes in and the red kind of goes almost straight through, and that's a longer wavelength. And the blue or the purple gets bent a lot. Those are the shorter wavelengths. They get bent quite a bit. So that is this idea of this dispersion. And we can use this effect to determine what kind of light is in a certain kind of light, what colors or what wavelengths of light are present in any given light. So here's an example of this. We have a Bunsen burner burning something like methane gas, and methane gas does not put off all of the light of the spectrum. It's not a perfectly white flame that it creates. It's kind of a bluish flame with some yellow in it as well. And so when you put this light through a prism, you get a spread of colors, but there's gaps in the spread. You get this dispersion, but there's gaps in the dispersion. You get a little bit of white, you get a little bit of red, a little bit of orange, a little bit of blue, a little bit of purple, and they end up being in these lines with these kind of black spaces in between. And why is that? Well, the reason for that is because different materials give off different kinds of light when they're hot. Now, the sun has just about every material you can think of in it, and they're all really, really hot. And so when you get all the materials you can think of and they're all really, really hot, you get a rainbow effect that is pretty much continuous with no black spots in it. Very few black spots. Even if you look at the light from the sun, you do get some little black gaps, but they're very small. But for the most part, you just get a rainbow. But with simple gases that have just one element in them, for example, hydrogen, if you just look at hydrogen that's being heated up, that's emitting the kinds of light that hydrogen gives off, you get just 1, 2, 3, 4 visible bands of color. And helium, you get a few more, and the more complex it gets, you often get more and more complex, we call these spectrums, spectra. Spectra is the plural for spectrum. And for sodium here, that's one of the kind of weird ones where you'll only get one line here that's in the visible range. But sodium has lots of lines outside of the visible range in the infrared and ultraviolet and beyond. But the interesting thing is that they were just kind of trying to figure out what these gases were all about, what they were made of, what was the difference between hydrogen and sodium, for example. And this helped them to figure it out. What they discovered from looking at these spectra and what they decided, they learned, they created theories about, is that each one of these atoms, each one of these different elements has different energy levels that their electrons exist in, and that these different energy levels give off different colors of light. And that's exactly what these lines represent. They represent an energy level that the electron jumps from or to, and as it jumps from one of these energy levels to another, it gives off light or it absorbs light, one of the two. When it jumps up to a higher level, it's absorbing light. When it falls down from a higher level to a lower level, it gives off light. So this is very important information, very important kind of discovery. The most common kind of rainbow that we see, or most common kind of dispersion that we see, is the rainbow in the sky. And this is caused by light refracting through little droplets of water in the sky. As the sunlight comes in, it's white light, and then it splits off into all the different colors, and then it bounces off the inside of the raindrop, and then it splits again as it's coming out, and we get this nice split of colors in this rainbow. But the interesting thing is that we actually only see half of the rainbow when we're looking at a rainbow. The other half is actually below the horizon. Rainbows always exist in these big donut shapes, these big circles with a hole in them. So that is the idea of the rainbow. If you ever have an opportunity to see a rainbow from a space station, you'll see it as a full circle. Another situation where you can see a rainbow as a full circle is at night. Have any of you seen an ice rainbow or a frost rainbow? Can't type sideways. Can't type normal ways, but let's see if we can get a nice visual of this. So this happens in North Platte actually fairly often in the winter time. This winter conditions weren't ideal for it, but if you have a nice icy night that's kind of humid but cold, where the air is really icy and frosty outside, you get those ice crystals in the air. Those little they act like little prisms in the air, and they create a circular rainbow around the moon like this, which is really quite cool. So if you're ever out on a frosty night in the winter in Nebraska, go out and look for that. It's fun to see. Then sometimes you can even see the primary reflection and the secondary reflection through the raindrop. Remember that there were two reflections and two refractions through the raindrop. One of the refractions actually can go through the raindrop and then get refracted again through other raindrops, and so you can often see the second rainbow out here. And you'll notice that the second one is inverted. The first one has its blue down on the bottom and it's red on the top. The second one has its red at the bottom and it's blue at the top. And that's because of that secondary reflection reversing the image. That happens with optics quite often, as we will see coming up. So now we're going to start talking about specific optics and how they behave. Spherical mirrors, first of all. So what is a spherical mirror? A spherical mirror is a mirror that is made from a part of a sphere. And here they've cut the sphere in half so that we're looking at the sphere as it's been cut in half from the side, and we're only seeing this one little edge of it. And if you take a ball and you cut one end of it off so that you've got a little bowl, and the inside of that ball is either the inside or the outside of that ball is covered in a reflective coating, then you would have what we call a spherical mirror. So a spherical mirror has what we call a radius, which would be the radius of the sphere that it was cut out of. And it also has a focal length, which is 1/2 of that radius. It also has a principal axis, which goes right down through that radius, through the center of the ball. We call that the principal axis of the mirror. And the mirror looks kind of like this, where it's like a bowl. It's either a bowl with the outside silvered or reflective, or the inside silvered or reflective. In this particular case, this mirror has the outside of the bowl silvered, so that it will be reflective surface. And you see these in stores all the time. They are used for security guards to watch for shoplifters, so that they can see around corners, they can see over the top of things, and they can see suspicious activity. Here is the equation that shows you that focal length is equal to the radius of that sphere that we took our mirror from, divided by 2, just something to remember. It's true whether or not if the mirror is concave or convex. In a concave mirror, we get this behavior where the light that is coming in towards the mirror if light is coming in towards the mirror and all of the light is parallel to the axis, the principal axis or the focal axis of the mirror, all of that light will focus to the focal point, which is half the distance between the face of the mirror and the radius and the middle central point, or the radius of the mirror. So that has a very interesting uses, of course. If you want to focus light to a point, a concave mirror is very good at doing that. Excuse me. A convex mirror, which has the mirrored surface on the outside surface of the sphere, will do just the opposite. Instead of focusing it, it will defocus it, and the light that's coming in will bounce off and spread out in all kinds of crazy directions. But if you took those crazy directions that it bounces off to and traced their paths back through the back of the mirror, you would find that they would all intersect at that focus, as long as the light that's coming in is all parallel. Now, the light coming in parallel is actually really important for these two behaviors. If the light's coming in at some funky angle, it will not focus at the focus of the mirror. Okay? So number 5 in the homework for this, let's see, we're in 7, right? Number 5 in homework 7. Yep. So we're about to get to that point, actually. This talks about things being upright or inverted, magnified, real, and virtual. We're about to get to that. So if you wait just a minute, we'll be there in just a second. That is going to be this next page here. So previously we talked about ray tracing and ray diagrams, and we're going to do the same thing with these mirrors. And what this is going to do when we use ray tracing with these spherical mirrors, it's going to help us to figure out what kind of images we can expect when we use different kinds of spherical mirrors. And here they give the 2 rules of ray tracing. The first rule is to draw a ray that is parallel to the principal axis reflected through the focal point, and that ray is going to come from a point on the object that you're trying to make an image of. So you pick a point on the object. In this book they usually pick the top of the object, and you draw a ray parallel to that principal axis and then reflect it through the focal point. And then for the second one, we're going to draw a ray through the center of curvature that is perpendicular to the mirror surface, and then reflect that back along the incident path. So let's see what they're talking about here. So here is a convex mirror. It has the inside of the mirror that is the actual mirrored surface, and here's the object that we're going to make an image of in this mirror. Now for this object we have 2 rays. The first ray, it goes parallel to the principal axis. The black line is the principal axis of the mirror. So it goes parallel to that principal axis, hits the mirror, and then it focuses to the focal point. So it turns so that it hits the focal point and goes right through it. Then another ray is going to come from that same point, and it's going to come down through the center of curvature. So that's at the radius, that's at twice the focal length. That's what they call the center of curvature, or the radius of the mirror. And it's going to come down straight through that and hit the mirror and come back. Now you should see from the law of reflection that both of these rays are obeying the law of reflection. This one has an incident angle. If you draw a line through here, an incident angle that equals its reflected angle. And this one over here has an incident angle of 0, so it bounces straight back. It comes in and hits the mirror perpendicular to the mirror, so it bounces straight back. Where these 2 lines intersect, where these 2 lines cross, is going to be where the point of your image is. So in this case, the point of our image ends up being down here, we're down here near the focus, and it's underneath the line, underneath the principal axis, and that's where the point of our image is going to be. And our object was this arrow, so we just make it this little arrow. Since it's beneath the line, since it's beneath the principal axis, that's going to tell us that our object is actually going to be flipped upside down. Our image is going to be flipped upside down. And that often happens when you're dealing with curved mirrors. The image often gets flipped upside down. That's what we call an inverted image. So if you do your ray tracing, and your ray tracing gives you a position underneath your principal axis when your object started above the principal axis, then you know your image is going to be inverted. Okay, the other thing that we're going to discover is that this image is much smaller than the object. It's much shorter than the original object. That means that the image has been reduced in size instead of enlarged. And that's what they're asking in this particular problem here. If they're asking if it's upright or inverted, this one is not. This one is inverted instead of upright. And then they're asking if it's magnified or reduced or the same size. In this case, it's reduced. Reduced, magnified, or same size. in the case of the example we're doing, not in the case of this problem. So in the case of this problem, this example that we're doing in the book, is this a real image or is it a virtual image? Now that's a little bit more difficult to understand. But for mirrors, the rule is if the image is outside of the mirror, in other words, if the image is on the same side of the mirror as your object is, this is outside of the mirror, then it's a real image. And that means that it could be projected. In fact, in other words, you could put a piece of paper here and you could see the image projected onto the paper. However, if the image is behind the mirror, on the other side of the mirror from your object, then it's a virtual image. It's not a real image. In other words, it can't be projected on paper. And to see it, you must be looking into the mirror. The only way that you can see it is by looking into the mirror. Now, your image that you see when you look into your mirror in your bathroom is actually a virtual image, because that image is behind the mirror, it's inside of the mirror, and you can only see it by looking into the mirror. For this image, for this situation, anyone could see it from any angle if it's projected. In fact, this setup right here is used in many situations to give people a virtual reality experience. So if you want people to feel like they're in a room with an object that is an actual three-dimensional object without using holography, then you can use spherical mirrors like this. We actually used to do this in our science building at the university I went to at Brigham Young University. They have a great big spherical mirror, and they have a dollar bill that is put out in front of the mirror that's hidden, but the image of the dollar bill is showing. And so people will walk by this little pedestal, they'll see a dollar bill on it, and they'll try to grab it, but it's not really there. It's just an image of the dollar bill. So it's kind of funny. So anyway, that is ray tracing for a convex mirror, which is fairly straightforward. Gives you an idea of what that's about. And there are many different situations that you can get with a convex mirror. With a convex mirror, if you bring in your object very close to the mirror and do your ray tracing, one of the rays has to go out from the object, hit the mirror, and go through the focal point. So it goes out parallel to the principal axis, hits the mirror, goes to the focal point, comes out here. The other one goes directly from the object to the mirror through the center point and comes out here. So this one actually has an image that's behind the object. Still a real image. This is the situation that we would use for the dollar bill. We put the dollar bill very close to the mirror, and then further away from the mirror we put a pedestal, and the image is real. It's upside down, but it's real. Right? So what we do is we put the dollar bill in here upside down, put the pedestal out here. People still try to grab the dollar bill. You can also make it so that they're the same size. They don't show that example here. You have to move this out a little bit further, but you can do that. In fact, I believe you put it at the center. If you put it right here, you'll get one that's the same size as the dollar bill. But here's another situation. If you put your object closer to the mirror than the focus, you put it inside of the focus, and then you do your ray tracing here, these rays never cross because they're diverging from each other. They're moving away from each other. They're non-parallel and they're never going to cross. So if you ever get the situation where the lines won't cross, then you have to trace those lines back to behind the mirror, and you will get a virtual image behind the mirror. And that virtual image can be seen only if you look in the mirror. So 3 different situations. First situation, you do your ray tracing, and you see an object that is smaller and closer to the mirror. And that's for an object that is outside of the radius. For an object that is inside of the radius but outside of the focus, you get an image that is further away from the mirror, and it is inverted, but it's still a real image. And for the situation where you put your object inside of the focus, close to the mirror, then you get a virtual image which is behind the mirror, and it is upright. You notice it's not inverted. And whether or not it's magnified depends on how far away it is, and it's in these different situations. All 3 of these situations are for a convex mirror that is silvered or mirrored on the inside surface. inside curvature surface. So here they do an example and they show us, I think, the picture down below here. Radius of curvature of 20 centimeters. Object placed 25 centimeters in front. No. Nope, wrong one. Let's see. Okay, so in this example here, they want us to actually do some ray tracing using this situation. Now this is the point at which I tell you it's probably a good idea to use a ruler, excuse me, and or some graph paper. Graph paper is very useful here so that you can tick off marks, and it doesn't have to be exactly 1 centimeter marks or anything like that. But graph paper is useful in these cases so that you can make very good diagrams, and it's good to have a ruler. I don't really have a ruler here. Let's see if I can find a ray tracing program online. They often have those available. Let's see if there's still one out there. Online ray tracing. Open it. Maybe. Dang it. No, can't use Java because this computer is stupid. Goodness. Online ray tracing. Here's one here's a good one. Let's see if it works. No, this is Java based again. The problem with doing things interactively online is that it's almost always Java based. In Java, they never update these computers for that. I should have brought my iPad in here. Let's see, maybe this one will work. See if Gizmo works. Hey, Gizmo's working. This is a lens. We need a mirror. Let's get a mirror here. No mirrors apparently. Let's see if they have one for. Let's see if they have one for lenses or for mirrors. Sorry. Ray tracing mirror. That's what we want. Good. I'll have to keep a note of this one. This looks like it's going to work all the time. Okay, so we're doing a concave mirror in this particular example, and so this could be very helpful actually. I'm going to make my lines different colors so I can see what I'm doing. My object is going to be this light bulb apparently, and my I need to move my focal point. Let's see what it says in the book, in the example. As a curvature of 20 centimeters, which means my focal point is going to be 20 divided by 2, which is 10 centimeters. So I think that my focal point in this one is 25, so I'm going to move it to 10 because that's what it says it's supposed to be, is 10. And then my object here, I'm just going to put it right on the thing so I guess it doesn't really matter. But let's go see where I'm going to put that. The object is placed 25 centimeters in front of the concave mirror, which means on the same side as that. So 25 centimeters, I put it right about here, right? And you can see the ray tracing. Now they've given me 3 rays. I don't need the central one because that's not one that we use in this class. But I've got the one ray that comes off the object, hits the mirror and it's parallel to the central line, and then it goes through the focal point. And then I've got the other one that goes through, in this case it goes through the focal point and goes over, and that works too. The one that we were doing before went through the center and then came back, and that would go right through here at 20 and bounce here and come back. They don't have that one. They have a similar one, but not the same one. So anyway, it's slightly different, but it still shows you that where they intersect, you get this object. And you notice that if I bring this object down, if I bring my object down to the center line, you can see that your image is going to be inverted and much smaller than your original object. If I bring it in closer, of course, my image gets bigger in my object than my object. So this one can help us to understand a couple of things here. First of all, they want to draw a ray diagram and estimate the image distance. So I drew my ray diagram, and you can use this online applet to do this if you want to. This little thing if you want. So the about the right distance, it looks like it's going to be going from 25 to 17 about. Looks like it's on about the second tick after 15. Don't worry about the negatives. That's not important. But, so that's going to be about 17. Let's see if that's correct for the estimated distance. R equals 20, 10 locations, C located. So figure 7.21. Let's see what they get for this. So they're drawing these things. This is the example. And they get the image coming in at, here's the original one, 25, the image coming in about 17, yeah, a little bit below 20. So that's about right. And it is inverted and smaller, just like we said. So that makes sense for us. Let's do one that is concave rather. No, convex. We just did a concave. So let's do a convex one. And this time, let's put our object really close into the mirror. And let's make our focus a little bit out here further. Yeah, let's put it out here. So this one will have a focus of 20, and our object, I'm going to put my object up here so you can see the lines a little bit better. But again, the lines, there's two lines that we're going to draw. The first line is going to be parallel to, it's going to come in parallel to the primary line. But since it bounces off of the mirror and goes off into oblivion, that one we're going to draw down through our focus. So it bounces off to oblivion, we extend it down to the focus so that we know which way it bounces off to oblivion. And then the second one comes in. Now the second one that we were supposed to do, we were supposed to come in straight and go through the radius, which they don't show that one, but the radius is out at 40, so it should come through about here and go straight through here. And so that one is going to also go through this point. Oh, I'm out of my user for that. But anyway, we saw from that one that the image was on the inside of the mirror, so it was a virtual image. It was a smaller image, not much smaller. Was it smaller or bigger? I can't actually remember. But anyway, could have been smaller or bigger. But anyway, that's how you do this. And you can do it online, you can do it on paper, but either way, the principles are the same. You draw those two rays, and then see where they intersect, see where the object or the image is relative to the object, and then use the rules to determine what's what. So a quick review of the ray tracing. I'm gonna write down some things for you to remember. Let's go to my EduCreations here. Did I start recording this class already this morning? I did. Oh, good. I was supposed to record today, this class. And why don't you remember that? I wonder if that's my password. That's not my password. Okay. So here is the ray tracing review, right? In ray tracing, we're going to make two rays. One ray goes parallel, there's the sign for parallel, to the principal axis. Hits mirror, and if no matter what, one way or the other, if the focus is in front of the mirror, which is the case for a convex mirror, then it goes to the focus. And if it's a concave mirror. If it's a convex mirror, then the focus is behind the mirror and it goes through the mirror to the focus. But either way, it hits the mirror and goes to the focus. For one kind of mirror, that makes a focusing ray. For the other kind, it makes a diverging ray, as they call it. So it goes to the focus. The other one, the other ray, is going to go directly from object. These both go from the object through the center, right? And then image forms where these cross. Image forms at crossing point. Right? Now, as far as figuring out what's what after you've done your ray tracing, first of all, real images are on the same side as the object of the mirror. They're out in space. They're formed on the same side of the mirror as the object. So, simple enough. Virtual images are on the opposite side, or the inside. They're inside of the mirror is what is the best way to describe it. They're inside the mirror. So you have to look into the mirror to see them, right? Of course, inverted objects are just upside down, inverted images are just upside down relative to the object, whereas upright are pointing the same direction. And then whether or not they're magnified or diminished, whatever they call that, enlarged or diminished, is just if they're bigger or smaller. And that's all there is to it. So now that we've gotten through that, is your question concerning these mirrors answered at this point, or do you need me to answer a different question or revisit something and make it more clear? Yep. So with the number, that's what we did with the ray tracing, and we can do that again really quick. So in this particular example, and I wish I could. I used to be able to choose graph paper to work with this, and I wish I had some graph paper, but I don't. So in this particular example, we have this mirror, this spherical mirror, and it has a focus that is at 10 centimeters, right? For mine anyway. Let's see what it says here actually. Nope, it's not. Its focal length is 36 centimeters. So let's erase that. So its focal length is 36 centimeters. I'm going to try to make this make sense. So this is going to be, let's call this 10, 20, 30, 40, 50. Okay, and so let's see here. It says that I have an object at 45 and a focal length of 36. much more precise if you have some graph paper or a ruler. But I've got 36 is about right here, so there's my focal point. And I've got an object that's out at 45, so that's right here. So my object is right here, right? So I've got to do some ray tracing. The ray tracing I've got to do is one of the rays is going to come perpendicular or parallel to the axis, hit the mirror. This is why a ruler is really nice, and go through the focal point right there. That's my first one. It's not exactly straight, but it's close. I'm going to draw my axis here too so that it becomes obvious what we're doing. So there's my first ray. My second ray is going to come from the same point, but instead of going parallel to the axis and then through the focal point, it's going to go directly through the center point. Now the center point is a different deal here. The center point is twice as far away from the mirror as the focal point, and so the focal point's at 36. That means my center point is out here about 72. It's out here about right here. There's my center point. And what this light is supposed to do is it's supposed to go up and hit the mirror that's up here. This mirror, I'm not drawing a very good mirror. And then it's supposed to go directly back through the center point. So I'm going to go up here, I'm going to hit the mirror, and it's going to go back. Now if I've drawn my center point to the right spot, going from this point out to the center point will give me, and I can't really show you, but out here over to the left here, it will give me a crossing point of these two lines, the red line and the green line, way out here, where this image is going to be created. And if you've drawn your line straight and you've made your measurements pretty good, then you should be able to measure from the mirror out to this point where they meet, out about here somewhere, and you should be able to get an approximate distance where those two meet. For the distances that I was given in my homework assignment, let's see, apparently, I'm in the student view. If I'm in the student view, I can't choose this one. If I'm in the classroom view, I can. In the student view, I can't choose to look at the answers. But I'm going to guess from looking at this that it's probably at about 100 centimeters out is where that image is going to be formed, and that's what I would put in there. Okay. Now, once you've got a number typed in there, if it marks you wrong, don't freak out right away. You may just be off by a little bit more than you should be. And you can always send me an email and say, how close am I? And I can take a look and say, oh, you're only off a little bit more than you should be, so that'll count. That's counts good enough. But if you measure very carefully, it shouldn't be very hard. The things that you have to measure carefully are the focal length out from the mirror, the center point out from the mirror, the position of this object from the mirror, and then all these lines have to be straight and parallel like they're supposed to be. So this one has to be parallel, this one has to be straight through the focal point. This one has to be straight from the object, straight through the center point, and then you see where they meet. And of course, you should be much more precise with your rulers and graph paper if you use it. Does that answer your question, how to get that? Okay. Good. So we started with mirrors, now let's move on to lenses. We've got to move quickly because we're running out of time here. Lenses come in a couple of different kinds as well. They come in a converging lens that focuses light and a diverging lens which defocuses light. And converging lenses are essentially kind of thicker towards the middle and thinner towards the outside, called convex lenses, and diverging lenses are called concave lenses. And we also use ray diagrams with these. And it's a very similar kind of situation where these lenses are also built so that you go through a focus. You go from your object parallel to the principal axis again, through the lens, and then once you go through the lens, you go through the focal point. And then with this one, instead of going through the center point or the radius point of the mirror, you just go through the middle of the lens. Just go from your object straight through the middle of the lens to the other side, and that's a straight line. The light that goes straight through the middle of the lens just goes straight through. And you can figure out what kind of image you have. Now, in the case of lenses, images are different. Remember, with mirrors, if your image was on the same side as your object, it was considered real. But it's different with lenses. With lenses, if the image is on the opposite side from your object, it's real, because the light actually goes through the lens. So in this case, the object is on the left side, the image ends up on the right side. It's a real object, it's a real image, and it's inverted in this case, and it may be magnified or diminished or whatever. But you can have the opposite thing happen. For example, here, if we put our object well inside the focus, very close to the lens, you can see that when we do our ray tracing, the lines never cross. And when the lines never cross from your ray tracing, then you need to do the same thing with mirrors. You need to trace them backwards and find the point on the other side of the lens where they meet, and then that will be a virtual image. And this is the case with eyeglasses. If you wear eyeglasses, the images that you see through your eyeglasses are virtual images. Because the object, the thing that you're trying to look at, for example, I'm trying to look at the screen on the other side of the room right now, that object is in front of my glasses. But as I look at that object, I need to bring it closer to my eyes because I'm nearsighted. And so my glasses are designed to create an image that is closer to me. The image is created about 20 centimeters in front of my face, and that way I can focus on it better. And I look through my glasses to see it. Virtual images, you have to look into the mirror. Virtual images, you have to look through the lens. So in the case of the virtual image, for lenses, it is on the same side as the object. It's just the opposite of mirrors. And that's what they're showing us here. Here is an example of a real image of a candle being projected onto a wall. Because it's a real image, you can project it onto something. It actually will be there. But a virtual image, here's an example of a virtual image. This virtual image being created by this lens being held up by this person, you have to actually look through the lens to see it. It won't be, you can't project that image onto something. It's only visible if you look through the lens, because the image is on the same side as the object. And that is how that works. Now, that is true whether it's a diverging lens or a converging lens. And you have the same ray tracing issues with diverging lenses as we had with diverging mirrors. You have the rays, when they go through the lens, don't meet. So you have to back trace them through the lens to find your image on the same side as the lens as your object. So lots and lots of ray tracing for lenses and mirrors. And that takes us to the end of our time, even though we haven't finished all the material. They talk about how lenses work in eyes, which is the same way as they work otherwise. And then we go into polarization, which I don't think that they give us any problems. The same thing with diffraction and interference. They don't give us any math with these, just some ideas. And so we don't have any real examples to do here. As far as I know, as far as I remember, I think I remember correctly, that is correct. So we've done all the examples that we need to do for you to get started on your homework. The rest of it is all just understanding concepts from reading. I apologize we didn't get through it as fast as we wanted to, as we should have. But next week when we do our lab, we will revisit these topics again. And make sure that you email me any questions that you have that you don't understand from things in the book, because I can help you with those. I will be very helpful since we didn't quite get to them. So, have a great weekend. We will see you later. If you need more time on the homework because you're not understanding something, please send me an email. We can do that too.
Can you do that? for me? Can I get like an extra like 24 hours?
We can extend this till Monday in case anybody has any questions.
Okay, because yeah, I have to like give someone a ride all the way to Holdridge, so then I have to
Okay.
work in the afternoon.
So homework 7, I'll just extend until Monday.
All right.
And since we didn't quite cover everything,
Okay.
in case you have questions on Monday, we can cover those.
All right.
All right, we need to get faster. All right, have a good weekend once again.